Okay, we're going to do a review that will help with the homework. This I'm going to do an example of an expenditure minimization problem. Okay, so first, the basic setup of an expenditure minimization problem is we say we're going to minimize. Let's just come up with two goods. We're just going to call them C and G. We're going to choose C and G to minimize our expenditures. So our expenditures is the price of C times C plus the price of G times G, subject to a constraint. And in this case, the constraint is we want to achieve a certain level of utility. Okay, so we want to find the lowest amount of expenditures that will allow us to achieve the utility that we want to achieve. Now let's say that our utility function is equal to the square root of C times G. Okay, so with an expenditure minimization, we're going to set up a Lagrangian function just like with utility maximization. And the Lagrangian function is the function of our two goods, C and G, as well as lambda. These are the variables of our function. And it's the expenditures plus lambda times the constraint. Okay, so when we solve this, what we want to do is we want to use our first order conditions, just like with the utility maximization. Three first order conditions. Derivative of L with respect to C. Derivative of L with respect to G. And the derivative of L with respect to lambda. Okay. Now, what I might do is just simplify this expression a little bit. Might make it easier. First, I'll distribute my lambda. You don't have to do this. Some people like to do this. There's a lot of variation. We can use different techniques to solve these. Okay, and then I'm going to rewrite this with exponents instead of the square root sign, because I think that with the exponents it becomes a little bit clearer. So then I'm just going to rewrite this as C to the 1/2 times G to the 1/2. So I just think that makes it a little bit easier. So then I'm just going to rewrite the whole thing here. All right, so here's the Lagrangian, which is the utility function basically simplified. That should make it a little bit easier. Okay, so we're going to take the derivative with respect to C. So what we'll just do is we'll go term by term, each term, taking the derivative with respect to C. So the derivative of the first term, PC. Second term, derivative with respect to C is 0 because there's no C in it. Third term, derivative with respect to C, 0 because there's no C in it. And fourth term, a little bit more complicated, but I'll go ahead and write it out. Okay, so one thing we do is we take everything that's multiplied by C, okay, and then we bring the 1/2 down, so times 1/2 times C to the negative 1/2 equals 0. Yeah? Now, I'm going to simplify this. Let's just simplify this. I'm just going to write it out again, but it's simplified. So when I look at this, I can see, okay, this C to the negative 1/2, I can bring that c to the bottom of this fraction. Then I can bring these guys to the top of this fraction. So then let's rearrange this. I'm gonna keep the lambda out of the fraction. That might make it easier. Let's see. So then it's going to be g to the 1/2 divided by 2c to the 1/2 equals 0. Okay. Now let's do our second first order condition. Take the derivative with respect to g. So derivative here, there's no g, so 0. Derivative here, we get pg. Come here, derivative with respect to g, 0. Okay. And come here. Okay, we've got this one again, so we'll do the same thing as we did before. So let's see, lambda c to the 1/2 times 1/2 g to the minus 1/2. All right, but I'll just rewrite it. We'll simplify it. pg minus lambda times, this time the c to the 1/2 is on top, and then it'll be 2g to the 1/2 equals 0. Okay, and then our final first order condition, it's just our constraint. Okay, now let's use our solution method where we solve the first two first order conditions. So first order condition 1, first order condition 2. Let's solve those both for lambda and then set them equal to each other. I'm going to do that down here. Okay, so solving 1 for lambda. I'm going to go step by step here. First thing that I'm doing is taking the PC to the other side. Okay, so I took the PC to the other side. Now I'm going to, I'm just going to notice that I can cancel the negatives out. I can cancel the negative signs out. That's equivalent to me multiplying both sides by -1 or dividing both sides by -1. It's the same thing, but I can just cancel those out. Okay. The next thing I'm going to do is I'm going to multiply both sides by 2c to the 1/2. All right. 1/2 equals 2c to the 1/2 times pc. Then I divide both sides by g to the 1/2. 2c to the 1/2 pc divided by g to the 1/2. Okay, now let's do this for the other one. So solving 2 for lambda. Same thing again. Okay, same thing as before. Cancel out the negatives. Multiply both sides by the denominator. Okay, then divide both sides by c to the 1/2. Okay. Now what I'll do is I'll set those two equal to each other and simplify. And I think we'll find that it simplifies pretty nicely. first of all, we can notice that, hey, this 2 is on both sides. We can just cancel those out. Okay. And then let's multiply. Let's multiply both sides by the denominators. Okay. This is going to allow us to get rid of the denominators, which will be nice. So we're going to multiply both sides by the denominators. We're going to get rid of get rid of the fractions. All right, so then these cancel out. And what are we going to find? We'll have c to the 1/2 times c to the 1/2 pc equals g to the 1/2 pg times g to the 1/2. All right, so now we'll notice that these simplify. That'll be c pc equals g pg. And so then we'll have c equals g pg over pc. All right, so then what we're going to do is we're going to plug that in to our last constraint here and solve for the optimal. And solve for g. Okay, so let's plug that in. So first I'm just going to rewrite it. Our last constraint's this. Okay, so I'm going to plug this in. Also going to convert this into square roots. So u bar minus g pg divided by pc to the 1/2 times g to the 1/2 equals 0. All right, now we're going to solve this for g. And that's going to give us our optimal g. Then we can take that optimal g and plug it back into the c. Okay, so here we go. We've got this. Let's just simplify it first by distributing. We're going to distribute some stuff. We're going to distribute this square root, and it might make things a little bit clearer what we've got going on here. Times g to the 1/2. 0. Okay, so now we can notice, hey, this g to the 1/2 is multiplied by this fraction. It's got g to the 1/2 into the top. If you remember this algebra rule, if I have a times a fraction, let's just say it's b over c, that's the same thing as a times b over c. Okay, so that means I've got this, g to the 1/2, so I can bring this up to the top, and then notice that, hey, it's g to the 1/2 times g to the 1/2. That means it's just g. So then why don't I rewrite this? pg to the 1/2 over pc to the 1/2 times g. All right, so I can bring this up or I can bring this down, either way, but I'm going to say that this g to the 1/2 times this g to the 1/2 gives me just g. Now this is fairly straightforward. I can solve this. Okay, so then we're just going to solve this for g. All right. Was negative utility bar. Let's cancel out those 1/2. Let's cancel out those negative signs. Multiply both sides by pc to the 1/2. All right, then we come down here, divide both sides by pg to the 1/2. And there we go. We've got our optimal g. Now now we can take that optimal g and we can plug it in to our c to find our optimal c. So let's do that. I'm just going to rewrite them here. So I've got c equals g times pg over pc, and my optimal g is u bar pc 1/2 over pg to the 1/2. Okay, so I'm going to plug this into here. So c equals So I'll plug this into here. Okay, a couple steps to simplify. I can bring these terms up to the top. So u bar pc to the 1/2 pg divided by pg to the 1/2, all divided by pc. Then I know from my algebra rule, I'll rewrite this algebra rule here. If I have a over b all divided by c, that's equal to a divided by bc. All right, so I've got a fraction divided by a number. I can bring that here. So then this becomes equal to this. All right, so now I just need to simplify this. I'm going to rewrite this down here. Okay, so now we're going to use this other rule. I'm just going to write the rule over here. If I have a raised to the b power divided by a raised to the c power, that's the same thing as a raised to the b minus c. So then I can rewrite this, and I can rewrite it as u pc raised to the 1/2 minus 1 times pg to the 1 minus 1/2. Okay. And say it's u bar pc to the minus 1/2 times pg to the 1/2. And then I can just simplify. Finding that that's negative, you can bring it to the bottom. So then here we are. This is C star. So there we go. Okay, so now we also might want to find what lambda is. So then let's find lambda. Now if we remember from earlier, one of our equations for lambda is this. We can plug our optimals into this. So let's find that. So lambda, here's an equation for lambda. 2g to the 1/2 pg divided by c to the 1/2. Okay, so now we're going to take g star and c star and plug it in for lambda. Plug it into the lambda. Sometimes I like to write big. Oop. It's a little bit easier. Okay, let's simplify this. So one thing I like to do when simplifying is we can distribute the exponents. Okay. So let's do that first. U bar, raise this to the 1/2. I'm also going to bring the U bar up. Oh, this is a 1/4. Okay, PG. Okay, I'm going to simplify that again. Make it into an easier fraction to deal with. I'll have 2 PG U bar to the 1/2 PC to the 1/4 over PG to the 1/4 U bar to the 1/2 PG to the 1/4 over PC to the 1/4. Okay, now I can take this, invert it, multiply it by the top. So that means we'll get this times the top. So it will have 2 PG U bar to the 1/2. That's a U bar to the 1/2, not a U to the negative 1/2, just to be clear. Okay. PC to the 1/4 times PC to the 1/4 divided by U bar to the 1/2 PG to the 1/4 times PG to the 1/4. Okay, so that we can simplify this. Cancel those out. Multiply these. Get 2 PG PC to the 1/2 divided by PG to the 1/2. You can simplify this further, recognizing that that I can write this PG as 2 PG to the 1 minus 1/2 times PC to the 1/2, which equals 2 PG PC both to the 1/2, which equals, just writing it out a little bit cleaner, PG PC. So that is my lambda star. So I'm going to write all my answers up here. So C star equal to U bar PG 1/2 PC 1/2. G star is U bar PC 1/2 PG 1/2. Lambda star is 2 PG PC. Okay. All right. So that solves for the optimal values for my expenditure minimization. Now, just to kind of review here, the expenditure minimization gives us our compensated demand functions. So then this is my compensated demand function for C. So let's ask, well, what's the effect? Let's ask, what's the effect of an increase in the utility on consumption? Now, what does that really mean? What I mean by that is, if I wanted to achieve a higher level of utility, how would that affect the amount of C that I consume? So I take the derivative of C star with respect to U bar, and we can find that, okay, this is just PG 1/2 over PC 1/2, which is greater than 0, which means that if I want to achieve more utility, if the amount of utility that I want to achieve goes up, then the amount of C that I consume will go up because the derivative is positive. Okay, now let's say I wanted to find what's my expenditure function. Okay, my expenditure function, we can say E is a function of the parameters PC, PG, and U bar. Okay, that's my expenditure function. The expenditure function equals PC times C star plus PG times G star. So if I want to know what my expenditure function is, I'm just going to plug my optimal values in. So PC times U bar, or PG to the 1/2, over PC to the 1/2, plus PG times U bar, PC to the 1/2, over PG to the 1/2. So that's my expenditure function. Now I can simplify this a little bit, because I'm going to recognize something, and that is that I can simplify this PC and this PC using that same formula that I used before. Remember this one? If I have A raised to the B divided by A raised to the C, that equals A to the B minus C. So this PC is like PC to the 1 divided by PC to the 1/2. So that becomes, let me write it out. So I'm just going to simplify this. This becomes PG to the 1/2, PC to the 1/2. Okay? Now I'm going to come over here and do the same thing. Same thing. I can recognize that same thing here. So this becomes U bar, PC to the 1/2, PG to the 1/2. Well, these two are just the same thing. So I can just add them up. 2 U bar. And then I might even, well, let's see, let's write it this way. PG to the 1/2, PC to the 1/2. And I might rewrite this just in a way that looks a little bit cleaner. This is just a personal preference. I'm going to rewrite it back as a square root. There we go. So this is my expenditure function. What's an expenditure function do? An expenditure function gives me the amount of money that I will spend if the price of C is PC, and if the price of G is PG, and if the utility I'm trying to get is U bar. For a given set of prices and the amount of utility that I want to achieve, the expenditure function will give me the amount of money that I need to spend. Okay, so there's my expenditure function. Now, I might ask you, you might be asked, okay, demonstrate that duality is true. So let me write down right now what duality is, explain it for a moment, and then I'll come back to it in another video. Okay, duality is the fact that there is a relationship between the compensated and the uncompensated demand functions. Another way of putting it, that there's a relationship between the optimal values, what I find when I do a utility maximization and what I find when I do an expenditure minimization. These two things are related to each other. And here are the relationships. First, let me just review. When I do a utility maximization, I will derive what's called the value function. The value function, it's a function of the prices and the amount of income that I have, and it gives me, the value function tells me how much utility. It gives me some amount of utility. So for a given set of prices and a given amount of income, the value function tells me how much utility I get. So if the price of C is 5 and the price of G is 10 and I've got $50, this is how much utility I will get. That's what the value function gives me. The expenditure function gives me, if I have a certain price of C, a certain price of G, and a certain utility that I want to achieve, the expenditure function will give me the amount of money that I need to spend to achieve it. What duality says is that these two things are related to each other. So I can write this. If I have, okay, let me just write this out, then I'll explain it. I can plug my expenditure function into my value function. Look, so the value function is a function of I. I can plug my expenditure function into my value function, and I'll still get that same U. I will get U bar. I will get the amount of utility, that optimal level of utility. Same thing, but in the opposite direction. I take my expenditure function and plug my value function in for the utility. And this will give me I. This will give me this I. Okay, so I might want you to show that this is true, that these relations, these duality relationships are true mathematically. So what I'm going to do next is I'm going to derive the value function. I'm going to do utility maximization. I'm going to use the same utility function, use the same thing, do utility maximization, derive my value function, and then show that this holds. Okay, I'll do that in the next video.